Hi, everyone, and thank you for being here. Today we will be talking about some of the basics of distributed training, and these are fundamental aspects of a large multi-device training, which forms the basis for pretty much all the all or most of the data-driven training that is very essential for training any AI model, not necessarily transformers. So to put things into perspective, let's try to do some back of the envelope calculation, which are fairly easy and simple to do, to see why we must need distributed training. So for example, let's take one of the state-of-the-art cases like trillion parameter models, the large models that we find at our disposal through many chatbot applications. So a trillion parameter model represents something, a neural network, for example, or a transformer type architecture with a trillion parameter. And let's say we want to train using the FP16 data type. So for FP16, we would require 2 bytes for each parameter. And to store trillion parameters, we would require 2 terabytes of memory. Now, training these large models require a little bit more than just the parameters. We require gradients to find an optimal convergence point so that we can, with some confidence, say that our model has learned some stuff. The gradients needs to be stored for each parameter, and it takes roughly the same amount of memory. So we can say that for a trillion parameter model, the gradients would take another 2 terabytes of memory. So now what we are trying to do here, we are trying to solve an optimization problem at a very large scale. So we require optimizers, and optimizers need to store a couple more states so that it can adjust different things. And a typical optimizer is Adam optimizer, which stores 2 additional states. So that amounts to 4 terabytes of memory. And then one of the core parts of this training is to have activation for different parts of the network. And that depends on the number of layers you have in your transformer architecture, the sequence length of the inputs that you are giving, and the hidden dimension, like the representation of the tokens in some abstract space, the batch size of your data, and that would take roughly another terabyte of memory. So in total, we need at least 10.5 terabytes of memory if we want to do the end-to-end training of a trillion parameter model. And the largest GPU memory in offer is NVIDIA's B200 with 140 gigs. So clearly we need more than one GPU. Even if we target the largest publicly available model, the Llama 405 billion model, it would take 810 gigabytes of memory. So just for the parameters, and the rest of the optimizers and gradients will tag along. So we definitely need clusters of GPUs. But still, doing the brute force would probably not be optimal. So there are different type of parallelisms that has been invented and applied regularly. And you probably have heard some of those words: tensor parallelism, sequence parallelism, etc. And we will learn more about these in the next lecture of the series. Today, we will try to look at a particular scenario where we have our model small enough to fit on a GPU, but our data set is really large. And we need GPU compute to process this data. So this is commonly known as the data parallel training. And we have a couple of examples ready here, and we will try to work through them. So now, just before going into the technical details, I would like to tell a quick thing that's like the shortcut of doing this back of the envelope calculations and estimation quickly. The first thing we can try to remember is trillion parameter models. We are talking order of terabytes. Billion parameter models, order of gigabytes. If FP16 is the precision type you will be using, 2 bytes per parameter. So just multiply 2 bytes, 2 terabytes. If FP8, there will be 1 byte. And each lower precision could be going downhill by a factor of 2. So you can very quickly estimate the memory requirement from machine to machine, generations of GPUs. It's a fun thing to do, and we should try doing it ourselves. Okay, so now the first thing I would request is to try to clone the repo. The repo should be cloned from a login node, and I have pasted the links in a couple of channels in the Slack. So, and if your SSH keys are not set up, please try the HTTP clone. And while doing these in the background, also request for a compute node, because we have a number of people trying to access resources. We may have to wait on the queue for a little bit, which is very normal. So please try to submit one, and you will get an access to a compute node. So a compute node is, you can think of it as a computer with 4 GPUs. The login nodes does not have any GPUs, so compute nodes are actually used for compute intensive calculations. At this point, do we have any questions?
Yeah, we have a couple in Slack. One of them is instructions on how to set the SSH key afterwards, if you have anything that we could point to for that.
Oh, we have to work a little bit to do that, but sure, afterwards I can try
Okay.
Getting that
And
done.
yeah, and then one question is, what if we git clone on a non-login node? Does it have a negative impact?
So it could be, so the login nodes talk to the outside world through some proxies, and these proxies are set up at the system level. So in principle, you should be able to clone without any extra steps from your end. For compute nodes, as far as my understanding goes, these proxies are not set up, so you may run into permission issues, saying that cannot connect to the remote server. Please make sure the repository exists. So these type of errors are highly unlikely to happen if you try to git clone from the login node. Make sense? Okay, cool. If there are no more questions, I will move forward. And please feel free to interrupt me anytime anyone has a question. Please be vocal, raise your hands. And okay, so the first bit is how we can write a single GPU program using PyTorch. PyTorch is one of the more popular machine learning frameworks today. So we chose to use PyTorch to demonstrate a simple example. So we import torch and we set the device as torch, the device CUDA. This tells PyTorch that we have an NVIDIA GPU to work with. We set some seeds and then we try to generate our data set. So the idea is for deep learning training or any AI model training, data is one of the core components, and data can come from multiple different sources, images, texts, and multimodal training may allow you to leverage audio, video data. So here we are trying to simulate a data set which we make, which is basically full of random numbers, but set up in the correct shape as torch tensors, which are more commonly used in a standard transformer-based architecture training. So this torch random numbers comes with 3 indices. So we would go with batch first mode. So the first index is the batch. So we have 2048 samples. The second index is the sequence length. We have each sample has a sequence length of 1. Very ideal situation, but we will have homework assignments where we play with these numbers and see how it goes. And the third one is hidden dimension, sometimes also called as feature number, so which is the dimensionality of the abstract representation of one of these sequences. And similarly, we make our target data set, which just has the sequence length to be 20 and rest is the same as before. So you can sort of, it's like a very not so accurate or perfect analogy, but an analogy would be, so I am giving my chatbot an input with sequence length 1, and I am expecting an output sequence length with 20 something. So this is actually looking at a situation where we ask a very short question to a chatbot, and the chatbot gives us very long and lengthy and verbose answer. It's very common, happens to me a lot of times, so I thought this would not be a bad idea. And then we set these random torch tensors into a data set which is easier for PyTorch to manage, shuffle through, load, etc. So that calls the tensor data set method and takes source as an input and target as an input. And then we set up a data loader which take the full data set, and we can set the batch size, we can set up shuffling, how much shuffle we want, and we take the torch.nn.transformer as our model. So this torch.nn.transformer implements the original transformer model that came out in 2017. But there are many different variants of the standard transformer architecture available everywhere, but we chose it as a demonstration purpose, and it sets the basics. Then we choose an optimizer, and then we choose a loss that we would like to use. Now we call the train method and send the model to device. This is where we send our model to the GPU. If the model is too big to fit on a GPU, tensor parallelism might come into play, but that's for the next lecture. And now we are trying to implement the training loop. We want to go over our source and targets that is given to us by the loader, and we send source tensors and the target tensors both to device. So there is a little bit of a system thing to notice. is when we make these data sets, these random numbers, they are in the memory. And then we have to copy them over to the GPU memory. So there is an overhead there, just to keep our minds open about different things that are happening under the hood. Also, when we try to select the optimizer, we select a learning rate. The learning rate is basically steps which our optimizers take in a preferable direction in the search of a global minima, if I may say. Once we have the data, we calculate, we call in the optimizer, calculate the gradients, and then we calculate the output, we calculate the loss, and then we take a backward step to update all our parameters. And after that, we go to the next step of the optimizer. So this is at the heart of everything that we are doing and today. And this is at a very simple demonstration of really simple training loop in a single GPU. So now,
Before we move on, just a
yeah,
couple questions in Slack. One question was asking what the batch size was. That was up top.
yeah. So batch size would be the number of samples would be drawn out of your total sample set at each iteration by each of the processes. So for example, if you are using 4 GPUs to do this training, each of them would take out samples in a chunk of 32. So that would be your batch size. And like sometimes it can be called mini batch size, so that you can multiply 32 with 4 to set the global batch size. But the fundamental idea behind this batch size is how big a chunk you take out of your sample, of your full data set, whatever you like to call that. Does that make sense?
I think so. And then one final question is around syntax. Yeah, we have a yes in Slack. What is someone's asking what the plus at the beginning of a line means in this context, and maybe comparing it to something like what you might see in like a Jupyter notebook, recognizing that like all of this is sort of the same, it just looks a little bit different.
No, it's so the plus thing is, so I should have cleared it. Thank you for the question. So it's the lines that you would add extra when you are trying to run on a GPU. For example, if you want to run this code on a CPU, you probably do not have to write these plus signs for the plus signs, plus signed lines in the first snippet. And also there is a pitfall there. So just simple copy and paste of these guys on your Python script may not work because I messed up with the plus signs and all. But these are the lines that you need extra so that your data gets transferred from CPU to GPU. Your PyTorch knows that you would be running on a GPU. Is that clear?
I think so. You can move on.
Okay, cool. And now, so let's say we have our single GPU code running on a single GPU. This is one of the homework assignments, by the way. So you have to make sure that this guy runs. So now let's say we want to do the training in multiple GPUs. So here are the plus signs are the lines or commands that you have to add to your Python code so that it is ready for a multiple GPU deployment. For example, the first thing that we do is we try to import MPI from MPI 4Pi. So why do we want that? So we want that to make sure there is a way we can talk to the many GPUs that we are using for the training. And then we import OS and socket. OS is basically trying to do system level operations that we normally may or may not use them. And then we again, and socket is to figure out the way, physical addresses that your node might use to talk to other nodes. And then after importing torch, we import the distributed data parallel method as DDP. This is the most critical component in setting up a workload that might span across multiple GPUs, even multiple nodes, hundreds of nodes. So the first thing that we have to be able to do is be able to aware of our size, how many GPUs we have, how many GPUs within the node, and one way of figuring that out is by leveraging MPI. So MPI can give us the size, and MPI can give us the global rank. I mean, for example, if you think of 2 compute nodes on Polaris, you have 8 GPUs. So global rank would go from rank 0 through 7. And now, based on however many nodes you have, this will be a finite list. And then we need also to figure out the local ranks. So for figuring out the local ranks, we leverage the parallel application launching service, so which is a tool from HPE available in the ALCF systems, and that allows us to communicate effectively with the job scheduler. So the piece of software that is taking this qsub command that we use to request for a node is PBS, and we need a way to talk to PBS, and PBS can tell us how many GPUs are within a node, and based on that we can calculate the local ranks. This can be done without the pals as well, and in one of the homework assignments we would try to explore that, how we can figure out the ranks that we need either using MPI or some parallel launching services that comes with the environment within which we are trying to deploy this workload. And also we have to figure out which would be our master node, so that we have a communication hub and most of the things will pass through that. And then we have to figure out a port through which there will be listening happening. So once we have figured out the environment, we are ready to set up and initialize a process group. All the collective communications involving the GPUs would be happening inside this process group. We can do communications by making subgroups within the larger process groups, and sometimes we may need to do that. But for today's activities, the activities at hand, we wouldn't need that. So the way we initialize the process group is we need to give the process group a backend. That means a library or a piece of software which will allow the process group to call different collective operation functions. And for NVIDIA based systems, that library is NCCL, NVIDIA Collective Communication Library. And then we also need to give it a method, which is basically all the environmental things that we have set up above. And then we have to give it the rank, because this initialization has to happen in each of the GPUs, each of the processes, and also we have to let it know the full size. Once we have initialized the process group, we have to assign a GPU to a local rank, which is done through the set device, and we also have to declare that this device to torch is a CUDA device. And once we have done that, we would choose the distributed variant of the samplers and the data loaders. Now, an important thing comes, the scaling of the learning rate. So when we try to distribute the training and we have multiple GPUs, at each iteration a larger volume of samples are being processed. 4 GPUs takes up 4 chunk. So total 4 chunk gets processed, and then when we average the gradient over this 4 chunk, the gradients become more stable, because average of a larger number would hide the fluctuations. But that is not the same as what we did with a single GPU. So as we scale up the number of resources, you can think of the gradients are scaling down in the same proportionality. So to restore the same optimization dynamics as the first and single GPU case, we scale the learning rate proportional to the number of GPUs or the total size that we would be employing. So in the document, I have given reference to a paper that came out of Facebook trying to explain the ImageNet training at a very large scale. And there this effect was empirically tested and results were reported. And that is nowadays known as the linear scaling law in deep learning. So we have to pay attention to that in order to converge to a global minima nicely. And then we do just set the epoch and let our sampler know that we would be running for these many epochs. An epoch is the time or iterations you need to run through your data set once, and then you shuffle it and do it over and over and over again, so that you look at all your data with roughly the same priority. So we have to let our sampler know, distributed sampler know, that this will be running for this many epochs, and then the regular part of the loop. And once we are done, we have to distribute destroy the process group. Otherwise, it might lead to memory leaks, and this can cause problems. Lingering processes at very large scale could be problematic for the cluster. So this is how we would set things up, tools to set things up at a larger scale, more than one GPU. Questions?
Yes, one question. How do you decide which backend to use? Is nickel the standard for all NVIDIA GPUs?
Yes, I think it is safe to say. But you can also use MPI backend, but then you have to source compile your PyTorch, and you have to set up the system in a way so that instead of using NCCL, your PyTorch looks for an MPI library and then use those APIs to call for different collectives. But it is very standard NCCL. Any NVIDIA machine you walk in, you want to do distributed training, you can pretty much expect and demand NCCL to be installed there in a nice way.
Excellent. Another question, can you talk more about what a memory leak is?
So a memory leak, you can think of a lingering process taking up your GPU memory. And that will be one way of thinking of memory leak. So once we call the destroy process group, PyTorch distributed would try to check and see if there is any work still happening in any other ranks that we have deployed, and it would try to gracefully shut down. Because in large jobs, it is possible that one of your ranks are a little bit slower than the other one for various different reasons. So, and that could lead to resource contention for a next process, for example. So destroy process group, and all these could be packaged into some version of memory leaking at a very high level. And destroy process group would ensure that lingering processes are not hanging around there.
Excellent. I think one more question before we move on. Why would one opt for PyTorch's DDP instead of Hugging Face Accelerate?
That's a good question. In principle, this example is simple and basic enough. You can probably rewrite it, reproduce it based on any of the framework of your choice, to be honest. There is no good reason for me to choose one over the other. But I can tell you why I chose PyTorch, because PyTorch is still used in many different contexts. For example, like graph neural network research. So, and other types of AI machine learning research. So PyTorch kind of can be established as a common thread for a very large number of people being familiar with it. So Hugging Face Transformer Library is probably more popular among practitioners of specifically transformer architecture and their variants. And so I wanted to bridge some sort of gap and increase the coverage. So that's why I chose PyTorch and DDP. You could obviously do it with any library that you like.
Great. I think you can move.
Okay, thank you. Thank you, Paige. So, okay, so now we have figured out and we have deployed our code, but we'd like to know how good our code is doing. So our code, it's one way of trying to find out how our code is doing is set timers. So you can call different timer functions that comes with standard Python and wrap your code block of interest with the two timer functions, and it will start a clock at the beginning of your loop, end the clock, you take the difference, you find how long does it take. But if we want to get a little bit of a fine-grained, like a little bit more fine-grained information, like some more, how is the data loading happening? Is the compute happening the way we would want? How are the communication kernels doing? You would try to do profile your code. And there are many vendor-specific profilers, but PyTorch profilers give us a way to compare the performance of this single piece of code across many GPUs, for example, Intel GPUs, AMD GPUs, NVIDIA GPUs. And it comes with PyTorch, so it's easy to use for quick investigation, something. And there are many information that comes from the profiler: operator execution time, stack traces, flops. The most useful is the execution timeline. So it will show you what happened in which order: forward pass, backward pass. And if you look at the profiler, you'd see a view of what's happening. And here I give a small piece of code of how we may enable the profiler. So in the interest of time, I would say that there are a couple ways, if not more, to enable your profiler. So, and the example that we have given is here we have enabled the profiler at the beginning of our training loop and finished it after the training loop. Why did we do that? We did that because first, our model is very simple, and we have very clear ideas about what are the data sets, how much memory, and it's not a very expensive model. So we could do that. But for very complex models that you probably might get from somebody else or you have developed yourself, end-to-end profiling could be very resource intensive. So in that case, you can use, oh, there is a typo in here. Sorry about that. Uh, you can use record function methods where you can profile significant parts of your code which you think might be taking up more resources, or you anticipate the communication pattern or the compute pattern could be more intensive than the rest of the code. So, and one caveat is that in this record function method where you profile snippets of your code may not work with the torch compile methodology, which is a relatively straightforward way to gain performance, although it is not promised to give you a better performance all the time. But in more often than not, you might find a torched compiled model gives you better performance, and the second methodology would not work there. So now we have all the nuts and bolts needed for simulating a situation closer to real life, and we would try to go over them very quickly. So in the example that we have looked at, we bypassed a very significant portion of a data parallel training, which is the I/O. So what we have done there is each of our ranks generated the data and put it back on the GPU for processing. In a real life situation, you may have to, or you are more likely to read from a data set that is sitting somewhere else other than your GPU, and you have to read from that file. You will probably not have the luxury to generate the data locally, and that can cause performance degradation, or instead of saying performance degradation, I should say it can lead to longer runtime of your application. So what we tried to do is gather the profiles, and I have given the examples, so you will be able to run these, generate these. So what a typical profile of the example that we are talking about when running on a node on 2 GPUs would look like this. So the chunk upstairs is basically your forward pass, and the chunk downstairs is your backward pass. And if you can see my cursor, this tiny block which is bordered with black lines is basically your data loader. So now we can click on that and look at how long it takes. So we find that the data loading takes roughly 1 millisecond. So now sorry for this, it just took me to the image. So now what we tried to do is use the same synthetic data that we generated, put it on a H5 file and tried to read from the file. And if we look at the profile, we find out that the data loading is 3 milliseconds. So that's like roughly 3 times increase just from reading the data. So this is one of the bottlenecks that are very commonly present in distributed training, and we have been able to see it for ourselves that reading from a file could lead to slowdowns. And now, so this is one. And the second important thing is the collectives. We have been talking about GPUs talking to each other, but in all the code pieces that I have shown, I have not done any collective communication because it was done for us under the hood by PyTorch. So now if we zoom in to the profile, we can see during the backward pass there are communication kernels that are being called, and this particular case it is an all radius. So it is basically taking the gradient information from all the GPUs available and reducing them to a number. And we can see that the communication calls are taking 1.5 millisecond each. Pretty like it's 50% of the data loading time. So again, we have the scripts to run these examples, and with these tools at our disposal, we have demonstrated two other many bottlenecks that are present in a distributed data parallel scenario. Okay, and the last bit is about torch.compile, and the torch.compile you can use it and see if this simple example gives you any benefit of compiling, because it can be an expensive process and it could take a bit of time if the model is complex to finish the JIT compilation and figure out the most efficient execution graph. Okay, so that's pretty much what I wanted to say. Questions at this point?
One question. Will you say what the profiling tool you were using? What was it? Will you just remind us what specific tool you were using there?
Yeah, it's the PyTorch's native profiler.
Okay, cool.
So when you have installed PyTorch, this profiler will be there. In case in the Polaris Conda environment, PyTorch is installed and it has the profiler.
Excellent. And then one other question. Someone asked, can GPUs directly read files, or do they have to first be read by a CPU and then transferred to a GPU?
To the best of my knowledge, it has to be done by CPU and then put it back to GPU. The data needs to be placed on the GPU for compute.
Okay, excellent. I think we can pop over to the hands-on.
Okay, so for the hands-on session, if you go inside the repo, you will see a whole bunch of Python files and a whole bunch of bash scripts. So there are two lines of action. One is testing the in-memory data loading, and the second is loading the data from an H5 file. And if you'll see Python files with PyTorch 2.8 DDP in the name, each of them implements data parallel. If you see an HDF5 in the name, that particular script is trying to implement data loading from H5 and corresponding job script there. And if you see prof, that means that script is trying to set up the profiler for you. And finally, if you see compile, that means that script has set up the torch.compile for your model. And we have made each of the script and job script independent. So you need a Python script and you need a job script to launch. So these two comes as a pair, and each pair is independent of the other. So these scripts should run in any order, but I would recommend going over. First you do the DDP PyTorch, just the DDP in-memory data loading, and then you do the loading from the HDF5, and then you run the profile for in-memory and run the profile for HDF5, so that you have something to compare against each other and see how things look like. And also, all the scripts that are not doing profiling are set up to run at any scale, any. But the profiling cases are set to profile 2 ranks on a node. It would be a very nice exercise if you try to set things up for the same 2 ranks, but 2 ranks now are sitting on 2 different nodes. And then you can see the communication kernels taking a little bit longer than the single node case. So I have also tried to set up some homework problems that I would like you to try when you have a free time. And please post issues, problems in the Slack, and I will try to be mindful and try to answer the questions. So the first thing that I would try to do is I would start playing with the different dimensions of the source and target tensors that we made. Make them really big, really fat, and see what it feels like. And also, I would try to use other file formats like npz or .pt, like some other file formats you will find, and see if you can make them work, and if there is any difference when you profile them. Do you see things better or worse? Make some reason about them. And these would be the first 2 that I would start working on. And of course, first you should make sure that the single GPU code runs on Polaris. And you can try to use the job script by changing the number of ranks and number of ranks per node to do a single GPU job as well. So these are the things that I wanted to discuss, and I hope it made some sense to you folks.
I think we have a little bit more time if you want to
Okay. Yeah. So now if it,
run through a
yep,
hands-on example
exactly.
for everybody to sort of see.
Yes. So let me try to find a. Can you guys see?
Yeah, there we go. Okay, nice. Okay.
Okay. So the first thing that I would try to do is cd into this directory. And then I would ask for a node. Let's see if I can get a node quickly. There we go. And I will so so now this one is showing that we have 3 GPUs, and then we are saying hi from rank 0. And so now we have started going through, and it takes roughly 5 seconds for the training to finish. So now let's try to run one of the profile ones. So these are just the 2 ranks. And you can see that the iterations are going a little bit slower, and it took roughly 11 seconds to finish that. The whole reason behind this is when a profiler is active, it tries to gather data from different components that they show us later. So if things have gone correctly, we should see a traces directory over here, and it looks better from the login node because we can now see different colors. You go into the traces directory, you will see there is a PyTorch 2.8, and it has a directory, and it has 2 files. So the JSON files are your timelines. I'll show them, show you how it looks like. Let's try to resize this thing a little bit. And then there are 2 text files. These text files actually give a summary of the things that has happened during the training period. So if I try to read one of the text files, this is all got pretty messed up, no? Okay, so now what this one is trying to tell us that which kernel, if I zoom out, it'll probably be a little easier to read. Okay. took the most time on average on the CUDA. No wonder the profiling took the most time. And then you can see the data parallel forward pass took the next most time in the GPU, and so on and so forth. And also you see the communication kernel all reduce shows up as well. So this gives you a summary of what's going on. And now I have some of the profiles loaded here. And this is how the profile looks like. And we can zoom into different parts and look for particular things. Here we were looking at the all reduced kernel. So you click on that, slices with the same name, you change the duration from larger to smaller, drag this thing back up, it shows you all the GPU kernels that has been called. You can try to count them and then see if these matches your expectation of one all reduce per iteration. So you can estimate the size of your data set, how many iterations we should need to go through given the batch size. Each iteration should in principle do one all reduce. How many had happened? Are the numbers going up, down? What is the trend? So this is how we can learn a little bit more about the workload. Okay, I think we have borderline time. Questions?
I don't see anything right now in the chat, but I would say if anybody has any specific questions for Khalid as based on what he talked about today, or as you're working through homework, feel free to drop them in the Slack channel for session 1. That's what it's meant for. And we can go from there. And then, okay, sorry, one question before we move over to Mengjiao. Could you repeat how to launch the profiler itself?
Oh, yes. So let's go to that. So here is the Perfetto. So once you have brought in those files to your computer, you can use the VS Code download, or you can do rsync. You open trace file, go to one of your locations, click on the JSON file, and it loads up. Okay, so once you have the JSONs, copy them over to your local somehow, and then go to Perfetto. I have given the link in the docs. Open trace file, select the JSON. It should load nicely. The browser-based profile viewer works pretty solid up to a profile that is 1.5 gigs. That's pushing the limits. But if you go larger than that, you may have to start running a local server, and then it becomes a little bit of work. But this one works pretty nicely.
Wonderful. Thank you so much for that.
Okay.
And there was a thank you in Slack as well.
Oh,
so I think with that, let's all thank Khalid for his presentation today. And again, as questions come up as you're working through things, please feel free to post them in Slack. But for our final bit for today, we're going to switch over and think about sort of applying some of this to more of a research space. So who we have presenter, and I'm going to introduce her, and then I'll let her get going. So Mengjiao Han is a postdoctoral appointee at ALCF, and is working within the Argonne Leadership Computing Facility, specifically within our visualization group. So her work focuses on scientific visualization with a particular interest in interactive flow field, so visualization, uncertainty visualization, and 3D reconstruction using deep learning. She received her PhD in computing from the University of Utah, and has previously held a postdoc at Los Alamos National Lab, so has seen many national labs at this point. So with that, I'm going to hand things over to Mengjiao, and she's going to tell us today about deep learning applications in scientific visualization.
Thanks, Paige. Thanks for the introduction. Let me share my screen. Can you see my slide?
Looks great.
Cool. So, hello everyone. My name is Mengjiao, and as the introduction, I'm a postdoc researcher at Argonne, where I work on visualization research. And today, I will be giving a high-level overview of how deep learning is being used to transform scientific visualization. And this talk connects the simulation science, artificial intelligence, and visualization. And we will explore how they come together to help scientists to better understand complex data. And let's start by looking at what scientific visualization really means and why it plays such a key role in modern science. So scientific visualization turns complex multi-dimensional data such as flow views, molecular structures, or astrophysics simulations into visual forms that humans and scientists can intuitively understand. And it's not just about making pretty images or videos. So the goal is to gain insight of the data, to uncover the patterns, make sense of the dynamics, and communicate the scientific ideas effectively. Typically, the workflow looks like run the simulations, save the data set, and then render the visualizations, then final analysis. And the images shown here illustrate some examples. On the bottom left, you can see a visualization of cosmology dark matter simulations. And in the middle, there's a visualization of Earth's metal. And the top right shows tumor cell trajectories. And the bottom right captures the airflow over an airplane during landing. And some of these were created by my colleagues in visualization team at Argonne. So this gives a glimpse of what type of work we do. So visualization in general helps us to review the hidden patterns in the data, test hypotheses interactively, communicate the results clearly, and even guide ongoing simulations while they're running. But as the simulation become larger and more complex, the traditional visualization methods starts to struggle, and that's where deep learning comes in. So the main challenges today are scale and complexity. So scientific simulations can now produce terabytes to petabytes of data, far too large to easily move data, store data, or visualize interactively. So traditional pipelines require reading all the data, rendering it, and then analysis, which is both slow and computational intensive. So on the top of that, many visualization tools require specialized expertise. So this means domain scientists who learn the physics and design the simulation usually cannot easily explore their data on their own. So this is where deep learning, or broadly speaking AI, starts to help. So deep learning models can learn compact representation of data, reducing the I/O and storage requirement. It can also approximate continuous fields or predict the derived quantities such as vorticity or pressure. It can replace extensive rendering steps, For example, very popular techniques like 3D Gaussian Splatting or NERF. And now, with the development of large language model, visualization can become more accessible. For example, instead of manually creating, like writing a visualization script or using visualization tools, scientists can ask AI, probably like show me the visualization at time step 500, for example. And let's look at how it's being applied in scientific visualization specifically. So here are several key areas where deep learning is already making a big impact, including the neural field representations, accelerated rendering, uncertainty and feature learning, in situ and interactive visualization, and AI assistant interfaces. So the two concrete examples are shown. I have shown in this slide. The top image shows like an implicit neural network, which encodes a scatter field of a human skull to a small neural network. It achieves up to 1,000 times compression ratio while maintaining the accuracy. And the bottom figure illustrates a model that predicts how the simulation would look under like different input parameters. So this approach helps quickly explore like quickly kind of like have a guess what might happen before running the costly simulations. So all these methods share the same goals using deep learning, speed, scalability, and accessibility. So next, I will introduce two projects we've done that apply deep learning in scientific viz. So our first example focuses on like interactively visualize the time-varying flow fields. So traditionally, we use particle tracing. This is a technique to visualize flow fields. It includes placing the seed points in the domain, then retrieve the velocity fields and advecting the particles over time. And this process is extremely computationally expensive. It requires large data movement, repeated access to the velocity field, and costly advection steps, especially for unstructured grade. So our approach replaces this entire process using a deep learning based model. So the model learns to predict the path lines directly from the flow field, which means instead of reading the massive velocity database and advecting the particles, we can infer the trajectories almost in real time. So we then integrated this model into a web-based visualization interface for interactive exploration. So this is a screenshot using a dataset called scatter flow. And on this web viewer, the model loads in about 1 second and visualize hundreds of path lines within just a few seconds. And this makes the flow analysis far more accessible to domain scientists. They can visualize and explore large flow datasets even using their laptop without needing some knowledge about visualization or HPC. And our second example extends a powerful computer graphics techniques called 3D Gaussian Splatting or 3D GS to the scientific visualization. So 3D GS represents data using millions of Gaussian primitives, allowing real-time photorealistic rendering. As the video shows here, this technique takes some photos or 3D scans of the scene, and after training, it can generate realistic views from any arbitrary camera angle. You can even try it with your phone to create a Gaussian model of, for example, like your room or like some scans you have. And however, previous scientific visualization work with using 3D.js only ran on single GPU, which limited scalability for large HPC simulations. So we developed the first distributed multi-node 3D.js pipeline for high-resolution scientific visualization. So in our workflow, each compute node processes its own local subset of the data and trains its own set of Gaussian splats in parallel. And after training, the splats are merged globally. So as a result, on Polaris at Argonne, we achieved 3 times speed up using 8 nodes and nearly identical visual quality. If you look at the images on the slide, you can see the reconstruction looks almost like indistinguishable from the ground truth. So the benefit of these approaches are very clear. They enable real-time interactivity, use compact neural models instead of the massive data, save the storage and I/O burden, and integrate directly into the simulation workflow. But we also facing some challenges. For example, like training and data preparation are still computationally expensive, especially for large-scale scientific data. And models may not generalize across different simulations because they have different underlying physics. And most importantly is interpretability, how to understand the model results and like how much I can trust the result from a model. So this field is evolving rapidly, and there are some promising direction ahead. One is the hybrid physics with deep learning, such as the physics-informed neural network, which combines the physics equations with deep learning. At the top right, you can see an example of the foundation model for science from NASA. And it captures multi-physics relationship across domains. And then later, scientists can use the foundation model to fine-tune it, adapt it to their own task. Another direction is distributed and institute training, which takes advantage of large HPC system like the Polaris Aurora we have at Argonne. And we're also seeing the rise of the real-time digital twins. If you are interested in like robotics, it connect live like sensor data simulations and AI models for dynamic visualizations. And finally, we talk about like large language model. AI assistant visualization design is very popular. Well, where like user can easily create visualizations just typing some texts. Yeah, I think that's all for today.
Thank you so much, Mengjiao. If anybody has any questions, please drop them in chat. I think we have time for maybe a couple looking at the time. But I think maybe while people are asking questions on Slack, one question I had for you is, I feel like something that's really important in applying AI to anything is making sure that you can evaluate it and make sure that it's actually doing what you expect it to do.
Yeah.
Can you talk a little bit more about on one of the specific projects that you've been working on, potentially sort of how you were ensuring that essentially whatever deep learning model you're applying is actually doing what you expect it to in looking at the data that you have?
Yeah, I think it's on this side, I would say it's easier for visualization. Like you can compare the results of the visualization, but it's tricky to. I'm also working on some uncertainty visualization, but it's kind of tricky if you involve deep learning. You involved a new uncertainty, so it's it's kind of tricky how you can you know decide if it produced the right results. One thing is, but you can still like take a look at the visualization first and then quantify the uncertainties from the model, from the data, see if it's correct.
Cool. Okay. I'm looking if there are any other questions right now. I see potential typing. Um, Maybe one other question for you, as other people type is, I imagine, can you talk about sort of the maybe difficulties and challenges of working with folks from different domains on their visualizations? If you're not necessarily trained in chemistry, like how do you interact with a chemistry visualization?
Yeah, I think it's more like a interactive, involving process. So at first, they gave us their data. They probably describe like what's inside the data, what kind of visualization he's looking for, and then we create some prototype, some demos for them. Sometimes we can't find, the right camera angle, the right feature they're looking for, and then we kind of get feedback from them and then like update. I think in this process it's more about we are learning more about the simulations. Although I don't know the equations, but I know some like, oh, there's the pressure and the pressure should be higher in this area, or velocity should be like, more here. Yeah, it's kind of
Mhm.
like very interesting to learn different like domains.
Yeah. What one person asked, can you expand a little bit more on what uncertainty visualization means?
So uncertainty visualization, without deep learning, it visualize the so uncertainty comes from first like the sensor you have. If you kind of like capture the data, the sensor will introduce some noise. And another, when scientists doing on some like simulations, they usually need to run it multiple times using different input parameters, what they call like a star stage. And these ensembles, like the noise will introduce from the simulation equations. And the visual uncertainty visualization is how you can visualize this kind of like uncertainty from the data or uncertainty from the model. So scientists will know how much I can trust their simulation, or if this area of data introduce more uncertainty, how can I fix it?